Yeah, very good morning to one and all. So myself, Arun Kumar K, Assistant Professor from Aeronautical Department in MLR Institute of Technology, Hyderabad. So in the previous lecture, we discussed about basic law of thermodynamics. We have discussed about zeroth law of thermodynamics and first law of thermodynamics with respect to the closed system we have discussed. We have discussed about the basic energy parameters also. In today's lecture, we are going to discuss about various quasi-static process and what is meant by quasi-static process and why we require this process. So let's start the session. See, so the quasi-static process. So from the definition itself, we'll come to know the quasi-static process is a thermodynamic process that happens infinitely slow manner. So we need to consider with respect to the very slow manner for the system to remain in internal equilibrium. So this internal equilibrium itself, we can have two categories. One is nothing but non-equilibrium states and another one is nothing but equilibrium states. See, in the zeroth law of thermodynamics, we discussed about equilibrium conditions. See, when we can able to define a particular state like initial state 1 and final state 2, there actually the thermodynamic macroscopic property remains constant. For example, before starting the process, I know the thermodynamic macroscopic properties. For example, we'll consider with respect to pressure, temperature and volume. So those properties are nothing but actually we are having a constant value, that is P1, T1 and V1 we are having. So this is nothing but actually we call it as the initial state. So the initial state, say for example, with respect to the PV diagram, I can able to plot P1 and T1 over here. This is before starting the process. That is what initial state. After completing the process, the system attains the coordinate as P2, T2 and V2. Right? So in the PV diagram, I can able to mention the coordinate 2 over here. That is what state 2. So the state 2 is nothing but your final state. This is your final state. State 1 is nothing but actually initial state. So in between that actually we don't know the points, intermediate states. So only we know before starting the process and after completing the process. That is why in this quasi-static process I have considered infinitely slow manner. So that is enough. That infinitely slow manner is enough for the system to remain in internal equilibrium. This internal equilibrium is nothing but actually we call it as intermediate states between the point 1 and 2, or we can say between the final and initial states, right? So this internal equilibrium is nothing but intermediate states. So for a while actually I am going to consider that is nothing but, for example, we'll go with respect to point A, that is very near to the point number 1, right? So if I have PA, TA and VA, right? So with respect to that, so with respect to P and TA, I can able to mention the coordinate with respect to the PV diagram. So over here, right? So that is your point A. Now I can able to join the initial state and the internal equilibrium state, that is point A, right? So these internal equilibrium states are required to find out the path of the process. See here, already I am having initial and final states only. So these initial and final states I can able to join, right, in any manner, in the linear manner or in the curved manner, right, with respect to any manners. So assume this is the path A and this is path B and this is path C. So I can able to connect the point number 2 or state 2, right, with respect to the various manner. but the particular process follows the particular path, right? For example, for simple example, let me tell you the constant pressure process. So if the constant pressure process, in the sense, we know that the initial state is 1 over here and the final state is 2 over here. So P1 equal to P2. This is your PV diagram. P1 equal to P2, so that I can able to join 1 to 2, right? So with respect to intermediate states also, the pressure remains constant. Got it? So I need to find out these intermediate states actually. This actually we can able to find out with respect to the mathematical way. So with the governing equation, we are having PV equal to MRT, the ideal gas equation. With respect to this, actually I can able to sense the mathematical governing equations, right? So this is the purpose of this quasi-static process. So for example, how to carry this quasi-static process and how to find out the intermediate states, right? So we'll go with the example. See, listen here. The equilibrium in a system in a quasi-static process is established many times more rapidly than change in the physical parameter of the system. So the quasi-static processes play an important role in thermodynamics, since the thermodynamic cycles including only quasi-static processes yields maximum work value. So whenever if we say the maximum work values, for the comparison purpose actually, this ideal gas equation I said. So the name itself actually we are having the ideal conditions. So for all cycles, for all thermodynamic cycles, we require only this quasi-static process with respect to the comparison purpose. So I need ideal processes and then I need the actual processes, right? So for that purpose only we are having this quasi-static process. So what are the processes? The constant pressure process, constant volume process, and the constant temperature process, isentropic process, combinedly we call it as polytropic process. So all this process comes under this quasi-static process. So mathematically I can able to find out the intermediate states. But for understanding purpose, see here how to find out the intermediate states. See in this first diagram, just see this diagram. In this first diagram, we are having the initial state. See here. So inside that piston cylinder arrangement, we are having the working substance over there, right? So there actually I am having the initial states as P1, V1 and T1. These are all initial states, right? And assume that we are having the constraint with respect to the piston cylinder arrangement, right? So the piston moves. This is your movable boundary. This piston is nothing but your movable boundary, right? So this can move with respect to the right to and fro motion. So here actually we are having the knobs. So with respect to that actually we can able to stop the piston movement. So assume that point is nothing but your final state. So until I supposed to add the heat energy, right? So I need to add the heat energy infinitely very slow manner, right? So for example, if I am adding 100 kilojoule of energy, heat energy to the system, what is happening? The momentum of the gas get increases. If the momentum of the gas get increases, it pushes the movable piston or movable boundary in the upward direction, right? So that the system reaches the final state once you're done with the 100 kilojoule. Got it? So above this piston actually I am having the mechanical weight over here, right? Above this piston we are having the mechanical weight. Assume this mechanical weight is nothing but in terms of mass we'll consider, right? Mass 10 kg for understanding purpose, or Newton also you can consider like 100 Newton or 10 Newton, whatever it may be, right? So I know only the initial states and final states with respect to this given system, right? So that I can able to find out point number 1 and point number 2. That's it. So in between actually I can able to join in any way. Instead of that actually assume this figure 1.7. See, listen here, this figure 1.7, right? So instead of the whole weight actually I'm going to consider with respect to I'm going to divide that mass into 10 parts. So this total weight equal to, so whatever the weight we have assumed, I have assumed in terms of mass, right? 10 kg. So assume that each slides actually we are having 1 kg, right? So each we are having with respect to the 1 kg. Now I said infinitely slow manner, right? We are adding the heat energy to the system in the infinitely slow manner. Say for example, this also I can able to divide like 100 kilojoule I am having. So I'll take the time taken for 10 minutes, for first 10 minutes. We'll add only 10 kilojoule. So the 10 kilojoule I need to add with respect to the 10 minutes. And again, next to 10 kilojoule I need to add in the next 10 minutes. Like that, if I keep on repeat the process, so that I can able to attain this intermediates. So this is a stopper actually, right? So there the final state we are having. So in between also, for a while it stays. And again, with respect to the another 10 minutes, for a while it stays. So which means we are having the internal, we got the internal equilibrium states, right? So if I got the internal equilibrium states, so that, right, I can able to find out the intermediate points also, like A, B, C, whatever I said, right? So that I can able to join all these points, then I can able to get the trace or path. Now this complete process I can able to find out which process it belongs, right? So this is the quasi-static process. See, the main purpose is nothing but it yields always the maximum work values, which is yields the maximum work values actually. That is nothing but the ideal conditions always gives the maximum work, right? So with respect to that, the actual cases I can able to compare. For that purpose actually we are having this quasi-static processes. Got it? So what are the various quasi-static processes we are having? See, with respect to this diagram itself I can able to say when pressure equal to constant and when volume equal to constant, like this, right? And for isothermal also mathematical relation. See here, for example I'll consider only with respect to the closed system, right? For a closed system, see, listen here, what is this ideal gas equation we are having? PV equal to mR into T. For closed system, mass is always conserved or constant. R is nothing but the universal constant. So this m into R I can able to write PV equal to some C into T, right? Got it? See, now with respect to this, see, with the PV diagram I can able to mention easily constant pressure process and constant volume process. For example, constant temperature process. So for that actually I can able to assume the temperature is also remains constant. So this constant into constant, some other constant, PV equal to some small c. So now I got the PV equal to C, right? So with respect to this, we know that PV equal to C in the sense P1 V1 equal to P2 V2. Similarly, with respect to intermediate points also, PA VA, right? So with respect to point A, point B, point C, point D and point D goes on. So like that actually we can able to find out the values, coordinates, right? So I have used only the ideal gas equation. So I can able to say this is nothing but the ideal conditions we are having or ideal processes we are having, right? So this is the purpose of the quasi-static process. So it is mandatory for the thermodynamic system to have the ideal conditions so that I can able to compare with the actual conditions. Otherwise I can't able to find out the feasibility, whether a particular mechanism or machines is able to construct or not, right? So for that case actually we require all these quasi-static process to frame the ideal cycles, right? See, these are the various thermodynamic processes, or we can say various quasi-static processes, right? So as we discussed earlier, so this is isobaric is nothing but pressure is constant, right? And isovolumetric is nothing but isochoric, right? Isochoric or isovolumic is nothing but constant volume process, right? And we are having the isothermal. See, isothermal process with the mathematical relation, it follows this kind of curvature. This is what isothermal. This is temperature equal to constant. This is pressure equal to constant, and this is volume equal to constant, right? And this adiabatic is nothing but actually we call it as, right, where the Q equal to 0. So for the rapid processes like compression and expansion processes, right, where the Q equal to 0. For this actually mathematical equation is nothing but we are having as you have studied in the intermediate level, PV power gamma equal to C, right? So it depends upon the Cp and Cv value. So that is why the specific heat constants are very important for the thermodynamic process. if I use a particular working substance. So this gamma equal to Cp by Cv. So it is varying with respect to PV power gamma equal to constant. That is what the adiabatic equation we are having. Right? So these are the various examples actually we are having. With respect to that, I can able to find out all the quasi-static process and all the ideal conditions. So this is for the graphical way, actually we are considering only with respect to PV. And similarly, actually we are having with respect to TS diagram also. Right? Once you enter into the entropy, that is actually we are having the next unit we are having as a second law of thermodynamics as well as third law of thermodynamics. Then we can able to enter into the entropy. So there actually we will discuss about the TS diagram also. For example, see, for all these ideal conditions, I have displayed only the two quasi-static processes. One is nothing but isovolumetric process, that is what pressure is constant, right? Sorry, volume is constant. When the volume is constant, see, with respect to that mechanical displacement, what is that mechanical displacement? Work done, right? So we discussed displacement work done and flow work done. So flow work done is applicable for the open system. For the closed system, actually, right? We are having, see, in the open system we are having flow work done as well as displacement work done. But in the closed system, actually, the boundaries are closed, right? So we don't have with respect to the which one? Flow system, flow work done. So that is why we are having only mechanical work done. What is that mechanical work done? Displacement work done. So that is integral PdV, right? Integral PdV. So in this dV is nothing but change in the volume, right? So in the change in the volume with respect to the constant volume process, the PV diagram, the change in the volume, what is that? 1 to 2. It is a vertical line. So 1 to 2 is nothing but V1 equal to V2. There is no change in the volume with respect to the path. With respect to this volume, I am telling, right? So there is no volume actually, there is no displacement also. There is no change in the volume, there is no displacement. Okay. So that I can able to say W equal to 0. Got it? And for constant pressure process, P equal to C. When P equal to C, while performing the integration, P I can take outside and only we need to do the integration with respect to dV, right? What is the dV is nothing but we are having del V. What is the del V? V2 minus V1. That is what del V. So this is your work done for the constant pressure process, right? So for constant temperature process also, see, for the constant temperature process also, I can able to derive, right? It's very simple to derive that constant temperature also. See, listen here. With respect to that, what we are having, formula is nothing but W equal to P dV. This is what your displacement work done. So when temperature equal to constant, right? So when the temperature equal to constant, what is the mathematical equation we got for the closed system? PV equal to C, right? MRT. Mass for the closed system is constant, and R is nothing but universal gas constant, and T is nothing but constant. So PV equal to C I can able to write. So then what is this P actually? P is nothing but actually we can able to write C by V. Right? So substitute this P over here. Now I can able to get the equation only in terms of which one? C by V dV. So that is dV by V. Right? So this C is nothing but constant parameter I can take outside. So dV by V is nothing but integral dV by V is nothing but natural logarithmic V. Right? So I can able to write work done equal to C into ln of V. So substitute this limits V1 to V2 volume changes. So ln of V2 by V1. This C again, this C I can able to write PV. What is the PV? Either I can able to write P1 V1 or P2 V2, right? So like that I can able to write with respect to the isothermal process also. So this is the work done, right? Similarly for the isentropic process, see, for the isentropic process the mathematical relation is nothing but what is that? Or adiabatic process, PV power gamma equal to C. That is what reversible adiabatic, right? PV power gamma equal to C. So here actually I can able to substitute P equal to C by V power gamma. So substitute over here, then I can able to write with respect to the adiabatic process, right? So combinedly I can able to write this as polytropic. Polytropic is nothing but actually for simplification purpose we have considered PV power N equal to C, right? When n equal to gamma, that is PV power gamma equal to C. So there I can able to say that is nothing but reversible adiabatic process, right? When n equal to 1, right, PV equal to C. What is that? Again, it comes under isothermal process. So then if I consider V equal to 0, n equal to 0, V power 0 is nothing but 1. So P equal to constant. For the infinity, V equal to constant, right? So like that I can able to get the various quasi-static process. So that is why we term this as polytrophic process. Right? Poly process actually inside we are having, it depends upon with respect to the index n. So this is what actually about quasi-static process. And so with respect to that quasi-static process, see, these are all got from always from the ideal gas, right? So that is the primary governing equation. With that actually we can able to plot in the graph, so that I can able to sense the PV diagram as well as TS diagram also. Got it? So this is about actually various quasi-static process. So thank you one and all. In the next lecture, we'll discuss about the numerical problem based upon this quasi-static process. Thank you.